Think we'll just give it a few more minutes to let people roll in.
Good.
All right, I think people kind of slowed down joining a little bit. We'll pick it off and let people roll in as they come. So get started. I guess a lot of you probably don't know me. My name's Adam Lowther. I do engineering sales with Odell in Waterloo. Started fairly recently this year. Just gonna be hosting this session, so thanks for joining us. Looking forward to seeing what we learned today. We have, I guess, 3 special guests now from Cambridge Air Solutions joining us. We have Jacob, who's an applications engineer with Cambridge Air. He's got some prior experience doing sales engineering. He's also been a manufacturer's rep before, so he's been around. He's seen quite a bit. And then we have Nathan with us, who's seen, he's got a background in aerospace and defense, industrial automation, all sorts of different manufacturing scenarios. He's also got a pretty wide range of experience. He's the new product and development and applications engineering team lead. So they'll be taking us away for this presentation. And then we also have Mark, who joined us, who's our customer sales support. So Nathan, I'll give it to you and get started.
Wonderful. Thank you, Adam, for the introduction. And also wanted to mention we have one of our great marketing folks, Brittany Walters, as well joined. So thank you, Brittany, for being here. And thank you all for joining us today. Just as mentioned, Jacob and I are on the applications engineering team here at Cambridge Air Solutions. We're located in St. Louis, Missouri. And what we're about is helping leaders in industrial manufacturing or warehousing create a better working environment for their people. And with our time today, our goal is to review the way we utilize technology, the way we utilize application methods in these typically high base spaces. And so hopefully we add some value, provide some options for solving customer problems in these spaces. And as we're going, we'd just love if you've got a thought, if you've got a question, feel free to throw that in the chat. We'll try to get through as many of those questions at the end if we can. And just to kick us off, I'll answer one question. Yes, I'm still recovering from the Blues loss in Game 7 double overtime on Sunday. And we'll just leave it at that. So with that, I'll pass it over to Jacob and you can kick us off.
Sure thing. Yeah, thanks guys for the introduction. Thank you all for joining as well. Very excited today to be speaking to you guys about how we think about solving industrial retrofit challenges. Just a brief agenda. We'll go over a couple different types of applications you may see, what technologies we think are most effective for solving those challenges, how to apply those technologies, and finally, we'll do some case studies towards the end of it. Once again, I'm Jacob Wyckoff. Nathan Ocker is going to be taking over about halfway through the presentation. Jumping straight into it, so there's really 2 key challenges we see our end users, contractors, and engineers face as they're taking a look at these industrial retrofit opportunities. So number 1, they have aging equipment in place that's nearing the end of its usable life. It's difficult to find parts. It's requiring more and more service every year. And taking a look at it, the end users and contractors are typically hoping first for a like-for-like replacement just to keep things simple. But after jumping into it, they realize pretty quickly that that's not the best way to solve it in most cases for a few reasons. So number 1, the use of the buildings probably changed significantly since the equipment was originally designed and installed. And as such, the needs from their HVAC system have probably changed significantly as well. Number 2, the building codes have probably changed quite significantly as well, especially surrounding mechanical ventilation requirements and on energy efficiency requirements. Finally, the existing equipment just simply may not be the best way to heat and ventilate that space. It may be dated technology that's inefficient. 15 to 20 years ago, we had less knowledge, so it may not be applied most effectively. So all of these reasons combine to really make us recommend in most cases to go back to the drawing board, assess the needs of the space as it is today, assess the technologies that are available today, and really come up with a comprehensive solution that's best for the end user now and in the future. The second challenge is ventilation and indoor environmental quality. Occupants and end users are much more aware of the importance of indoor air quality, both from a health standpoint for their people and from a regulation standpoint, and the liabilities that are associated with not providing that to their people. Also, part of indoor environmental quality is having a comfortable temperature for all of your occupants, which is hugely important in today's climate, to be able to retain and recruit employees, and also to be able to get maximum productivity from the people inside of your space. But we know that sometimes those come at a cost, especially from other applications that we've been looking at. So how do we square that with current trends towards decarbonization, towards rising energy cost, and towards a general focus on trying to limit the amount of energy that you use to heat and ventilate your facility? So we'll talk a little bit about that balance in this presentation as well. So when we take a look at these applications, we really separate them into two different paths because the way we look at solutions for these differ a little bit. So they are very similar types of applications. They're both large, open, high bay facilities, like Nathan said. As with all businesses, they're going to have the goal of minimizing both first cost and operating cost throughout the life of the equipment. But where they're going to start to differ is that warehousing and distribution type facilities are going to be very similar from building to building. They're not going to have much occurring in the space. They're going to have a few people, maybe a couple forklifts. They're bringing in goods, storing them, maybe repackaging them, and sending them out to another location. As such, it becomes much easier to give specific recommendations for most of these applications. The ventilation is pretty much always going to be driven by your ASHRAE 62.1 minimum ventilation requirements or from your lead building ventilation requirements. Whereas with manufacturing, your ventilation and makeup air requirements are going to be highly variable from building to building, depending on what's happening, what they're producing, what they're doing inside of that facility. So a paint booth is going to be different from a weld shop. It's going to be different from a location where they're manufacturing tires. And how does this play out in the way that we look at the HVAC system for these spaces? So with warehousing and distribution, we're primarily going to be looking at what's the best way to heat this space. We're going to optimize our equipment selection around heating the space efficiently and effectively. And then after doing so, we're going to make sure that we're meeting the ventilation requirements required by code for that space. Whereas with manufacturing, we're going to first look to cover all of the makeup air requirements of the space to be able to make up any exhausted air, control room pressure, things of that nature. And then after we have our equipment selected and optimized around that, we're going to make sure that we are able to meet the heat load of the space somehow. So jumping first into the manufacturing type path that I mentioned, examples like building facilities, paint booths, tire manufacturing, things like that. You can see in this GIF right here, we have equipment down in the space and people down in the space. In this instance, that equipment is giving off some harmful gases that would be harmful for the people to breathe on a consistent basis. Due to this, we need to exhaust that air out of the exhaust fans you see over there on that wall. And anytime, especially in a cold climate like Canada, you are exhausting air, you need to make up that air through either tempered makeup air or heated makeup air. Otherwise, you're going to get a negative room pressure that's going to be sucking in untreated cold air from the outside, which is going to cause a whole host of issues to your building. So we know we need to make up that air somehow. And we typically see direct fired makeup air units being the most effective way to provide this tempered or heated makeup air. If you work in industrial facilities quite often, you're probably already familiar with direct fired makeup air, or if you've ever worked in a kitchen type environment as well, pretty common for your kitchen type applications as well. We really see these in your high outside air applications for a few key reasons. Number one being that they're highly efficient. They're the most effective way to heat a space using natural gas. Because you have that combustion process directly in the airstream, you have no flue to lose any heat, and you're going to get that great 92% thermal efficiency out of the heater and 100% combustion efficiency. Another huge reason that they're used in these applications is that they're able to process large volumes of outside air, even at very, very low temperatures outside. So that's something that indirect fire technologies and electric technologies especially can sometimes struggle with, being able to provide the needed heat on the coldest day of the year. Another reason is that they're typically pretty low maintenance, simple, relatively low first cost pieces of equipment that are able to be reliable and last for a very long time. So these manufacturing facilities, they want to focus on making the goods and products and services they're doing in the facility. They don't want to worry about what's happening with the HVAC equipment outside. They just want to make sure that it's going to start up and operate as it did the same the day it was installed throughout the life of the piece of equipment. So like I said, your manufacturing facilities are going to vary pretty greatly from building to building, so it's tough to give too much specific advice. But these are just some general things that you want to be thinking about early when you're going about these industrial retrofit opportunities. So number one, how are you going to control the heat of that makeup air unit? Do you want to control the discharge temperature where you're modulating the burner to be able to maintain a specific discharge temperature? In most of these cases, you're going to be providing room neutral air to make up any exhausted air that's happening inside the facility. Sometimes you're going to be controlling the temperature of the space through other equipment, or oftentimes discharge temperature control units will have a routine that if the space temperature drops too low, it'll increase the discharge temperature by a set amount. The other option is space temperature control, where you modulate the burner to maintain a constant space temperature by increasing or decreasing the discharge temperature within a range. This is great because it allows the makeup air unit to directly control the temperature of the space and is a great option whenever you want tighter control over the temperature within the space. The second thing that you want to be thinking about early is how are you going to control the airflow? So most of these manufacturing type applications are going to call for variable airflow needs of some sort. There's a few different ways to go about this that we see commonly. So number one, room pressure control. You have something in the space that's directly measuring the room pressure of the space. And the unit's going to vary the CFM depending on that measured room pressure to attempt to control to a slight positive pressurization in most cases. Number 2 and 3, analog input from external sources and exhaust fan interlock. We use these when the equipment is going to be tracking with exhaust fans with an analog input that's typically going to be tracking with variable speed exhaust fans, whereas an exhaust fan interlock is going to be tracking with a variety of exhaust fans that are cycled on and off. And then manual speed control is a great option if the unit does not call for variable speed today, but you want some flexibility in the future. You want the ability to test and balance the unit, and you want some flexibility in the future to maybe add some filtration. Maybe you want to, maybe you remove a weld booth in the future and you want to decrease the CFM slightly. Having some variable speed options, even as manual speed control, can be great to provide the user some flexibility. Another thing to think about is where are you going to put this unit? So in most of these industrial retrofit applications, we're really thinking first about minimizing the disruption to the facility. That square footage inside is extremely valuable, and we want to let the facility have that space to do their manufacturing. So typically this results in mounting the unit outside. This is great. You want to consider the ease of installation as well. You want to locate the unit. If you have an existing unit, you want to locate the new unit near the existing gas and electrical connections if possible. This can reduce the amount of gas piping, electrical you need to run, lower the install cost. You want to minimize the ductwork. So you want to locate the unit near where would be a good place to immediately discharge the air into the space. This is going to save you some money on ductwork, and it's also going to reduce the impact of ductwork on the facility, as you no longer have to worry about forklifts hitting that ductwork or worry about interference from some tower cranes that might be happening in there. We also see in these industrial retrofit opportunities, mounting the units outside on the stand or a pad or as a vertical unit on some legs in order to minimize the crane requirements. So it's going to require a much smaller rigging equipment like a crane to be able to set a unit down on the ground on a pad as opposed to setting it up on a roof. And in many cases, these industrial facilities that have been designed for 50 plus years, they don't have the roof design to support structural HVAC equipment. So it would require a lot of reinforcement to be able to set HVAC equipment on the roof. That's why in most of these industrial retrofit applications, we're seeing the unit on a pad just outside the unit and immediately ducted in and having that air thrown across the space. You also want to think about ease of access and serviceability for the service technician. You want to make sure they're able to access the unit, preferably from the ground. As you can see, pad-mounted units are great because the service technician is able to access the control panel without getting up on a ladder. Whenever you get vertical units or units on very tall stands, you start to get into ladders and catwalks to be able to repair the unit. And sometimes this is necessary, but if you have the footprint outside, a pad-mounted unit's a great thing to consider as well. And for air distribution, you want to minimize ductwork where possible. As I mentioned, this is just going to reduce the cost of installing ductwork and also reduce the chances of that ductwork getting hit by a forklift or some other things happening in the space. Really, whenever you're thinking about air distribution, we really want to make sure we get that fresh air down to the occupied space. We don't want to be short cycling that fresh heated air straight through an exhaust fan. We want to make sure that fresh air gets down to the space where the people are at, and we're evenly distributing the heat throughout the facility so that all the occupants are comfortable in that facility. So, there's a variety of diffusers and plenums that you can take a look at to achieve this. Some people utilize some fans within the facility to be able to achieve this. There's a lot of ways that you're able to go about doing this. Even the location of the exhaust fans and the relief is very important because the air is going to tend to flow out of those exhaust fans and that relief. Now, what about warehousing and distribution? As I mentioned, it's much easier to give specific guidance in these warehousing and distribution applications. We consider HTHV to be the best way to heat and ventilate these warehousing and distribution type spaces. So what is HTHV? HTHV is actually a definition created by the Department of Energy with specific performance requirements. That definition is high temperature heating and ventilation units must be a 100% outside air direct fired heater with greater than 140 degree temperature rise, greater than 150 degree discharge temperature, and it must have fully modulating temperature controls to be able to meet both ventilation and space heating requirements. So, similar to a makeup air unit, HTHV units are going to be 100% outside air, direct fired pieces of equipment. You're going to get that great direct fired efficiency of 92% thermal efficiency because that combustion is happening directly in the airstream and you don't have any flue losses. Makeup air units, as you can see, is going to have that blower downstream of the burner with that blower in the hot air stream. And this is fine when your main concern is providing large amounts of makeup air and your discharge temperature doesn't need to be as high. But when you have that blower in the hot air stream, you're going to limit your discharge temperature to anywhere around 120 to 140 degrees. That's just because the blower components really can't handle going above that by much. So your belts, your bearings, your motors are only rated for specific temperatures, and trying to run those even at 140 degrees and especially greater than that is really going to reduce the amount of life that you're going to get from those components. And you're going to be frequently replacing components much more often than would be reasonable. So what HTHV units is they actually flip where the burner and the blower are in the airstream. So the blower is moved upstream of the burner into the cold airstream. And what that does is it allows HTHV units to discharge at a much higher discharge temperature reliably and consistently year-round. So when you put that blower up in the cold airstream, that's going to have huge impacts on the ability to heat the space efficiently whenever you no longer have that restriction on discharge temperature. And we'll go through why that is later in a few slides. So one question we get often is how can it be efficient to use outside air to heat? We know from other applications how expensive it is to heat or to provide large amounts of outside air. Why is it different for these warehousing and distribution type spaces? Why are we heating so efficiently using outside air? So we know that every building is going to require some level of outside air for human occupancy. We know that from ASHRAE 62.1 building codes. Every building is going to have to get that air either through mechanical ventilation in most cases, in most places with modern codes, or from natural infiltration. So even if the building does not require mechanical ventilation, it's going to have air infiltrating into the space somehow. And if you were to provide mechanical ventilation through 100% outside air, you're going to positively pressurize the space and reduce the natural infiltration that would have otherwise been occurring. When we talk about heating these spaces using 100% outside air, it becomes much more simpler to talk about it by separating the air load, which is that outside air that needs to be heated as it comes in or when it's in the facility. And the rest of that heat load being the conduction losses, your conduction losses, the skin losses through the walls and roof of the building. Those can vary between about 30 to 70% each. So what's the most efficient way to heat the air load? We know this, especially from kitchen applications, to be direct fire. Those are very cost sensitive applications, and they definitely want the most cost effective and energy efficient way to heat the air load. Pretty clearly, it's going to be direct fired because of its improved efficiency, its improved simplicity over indirect fired technologies. It has no flue losses, and it's going to require 100% outside air makeup air, but that's fine because in this instance, we're only talking about air load. So let's take this example of 10,000 CFM of 0-degree air entering the unit and discharging at 70 degrees. This is the most energy efficient and most competitive first cost way to heat an air load. Remember this example because we'll come back to it in a couple slides. And what's the best way to heat the conduction load? So you can add an indirect fired system at the efficiencies we talked about previously. You're going to have the flue losses, but the benefit theoretically is that you can recirculate the air through that indirect fired system, recirculate the air that's already in the space without having to heat any more outside air. Another option is to simply turn up the discharge of that 100% outside air direct fired system that you already had to heat the air load. You get the direct fired efficiency, you lose all those flue losses, and every degree you raise your discharge temperature above the space temperature, you're going to get heat that's usable to cover the conduction losses of the space. We call those usable BTUs or net BTUs. So take that same example we had previously of a 70-degree discharge unit. It had 869 MBH of heat output. If we raise that discharge temperature all the way up to 160 degrees, you can see now we have 1987 MBH of heat. That difference between 1987 and 869 MBH due to raising the discharge is going to give us, in this case, 1100 MBH of usable BTUs because we're raising that discharge temperature by an additional 90 degrees above the space temperature. It's going to give us 1100 MBH of BTUs that are usable to cover the conduction losses of the space. So this slide right here does a great job of really showing the high importance of high discharge temperature. So take that example where we have an 1100 MBH conduction load of the space. If we allow ourselves to discharge at 160 degrees, we know we're only using 10,000 CFM to cover that conduction load. But if we have a draw-through style unit where we're restricting the discharge temperature down at 120 degrees, now it's going to require 24,000 CFM of outside air to be able to cover that heat load because we're only getting 492 MBH of usable BTUs per every 10,000 CFM that we provide. I think we see where this is going. Whenever you restrict the discharge temperature and have much more CFMs, it's going to have larger equipment that's more costly to install. But more importantly, you're going to be wasting energy as you are having a much larger fan that needs to run. And more importantly, because you're wasting fuel treating a large amount of outside air that's way above any ASHRAE 62.1 minimum ventilation requirement you might see in a warehousing or distribution type space, which is going to be much more costly for the user and the much less efficient way to heat that space. Another question we get often with HTHV is how do we avoid stratification when we're discharging 160 degree air? We know that these high bay spaces are especially susceptible to stratification. They have very tall ceilings. They have cold air infiltrating down near the floor through open dock doors and man doors. Can oftentimes result in stratification, especially if maybe they're heated by something like unit heaters, which have trouble getting the heat down to the floor and mixing the air throughout the facility. That's going to result in the people down in the occupied space being cold, the thermostats reading a cold temperature, which is going to keep the equipment running for a long time. And you're going to have a very hot roof line, that's going to basically increase the temperature difference between the inside of your roof and the outside of your roof, which is going to make you lose even more heat out of your roof than necessary. So we know that this is a huge issue in these high bay spaces if you are experiencing stratification. So how do we avoid that? So other technologies often consider things like HVLS fans, pair fans, or zoo fans to get that heat from the ceiling down to the floor and to destratify that space. And this is great, but HTHV actually doesn't require that. So HTHV uses a high velocity discharge, anywhere from 1,500 to 2,000 feet per minute, that's able to destratify and mix the air within these spaces. It's going to discharge the air at a 45-degree angle. All right, I thought I lost you guys. It's going to discharge the air at a 45-degree angle. It's going to sweep that air across the floor, hit that back wall, any throws of anywhere from 250 to 275 feet. It's going to hit that back wall, turn, and it's going to sweep and induce that stratified ceiling heat as well. So we often see a 10-to-1 induction ratio with these pieces of equipment, meaning for every CFM of air that the supply fan of the HTHV unit provides, it's moving 10 CFM of air that was already in the facility and mixing that air throughout the facility. Another benefit of 100% outside air units is that you are positively pressurizing the building, which is going to reduce that infiltration you're seeing down near the floor through those open dock doors. When applied correctly, HTHV is going to see anywhere from a 2 to 3 degree temperature difference from the floor up to the ceiling and across the walls. So that's how we avoid stratification in these spaces. I'm going to pass it off to Nathan Ocker, and he's going to take over from here. Thank you all for your time.
Thank you, Jacob. And as we look at these destratification technologies, there's really a massive value. There's an impact for the money. And so in this example, we could see one 1600 MBH HTHV unit compared to 6 unit heaters, one HVLS fan, maybe multiple HVLS fan, and then also a dedicated outdoor air system. So what this means, what this really gets at, other than a value for money, is you have simplicity of design. And so when we're trying to develop a solution for a customer, the key thing we want to deliver is the most simple design that meets their requirements. There's a lot of benefits to this. So you get a single piece of equipment versus multiple pieces of equipment, single electrical connection versus multiple electrical connections. You've got single wall penetration, potentially 0 roof penetrations, depending on mounting configuration. And so as you look at this, this really gets at improving the integrity of the building envelope. And if you've ever had to deal with water through a roof, water getting into a facility, managing that with a customer, it can be really challenging if you've got lots of locations. And so important to maintain that integrity as you're looking at a facility as much as possible. So we're looking at design considerations in distribution. Really want to break down the facility into zones, if at all possible, especially in an open space. Try to manage these expectations within each zone. And so heaters really are best positioned, what we found, near greatest air load. And so you can see here, got loading dock doors on the top end, and these units positioned near those loading dock doors where you may have infiltration as they're open and shut throughout the day, as the facility's managing, moving their equipment around. And that really gets you, with that high velocity, incredible distribution from floor to ceiling and all throughout the space. When we look at these facilities, there's lots of constraints around positioning equipment potentially, and that may even inhibit the ability to deliver the right piece of equipment if you can't find a mounting location that can work for the customer's needs. And so as we look at these mounting locations, having options, whether through wall, rooftop installation, maybe even under roof, depending on the customer needs. And some vertical installations can also be particularly useful in certain applications. Considerations around these are install cost, maintenance location. What is the best for maintenance location for a facility? Even snow or water ingestion can be considerations depending on these locations. So while flexibility for mounting location is important, it's really also important to consider a lot of topics that are forefront in the HVAC community around decarbonization, electrification, and what are the best methods? What is a cohesive strategy that can get at both the important goals of decarbonization and electrification to meet some of our society's needs, some of our customers' needs based on regulations or those kind of things. So looking at decarbonization, of course, reducing the total amount of greenhouse gas emissions caused by human activity. And then electrification would be, of course, substituting electric technologies for combustion for the existing combustion fuel technologies for end uses. And let's just look at an example here of a warehouse. So this is a warehouse in Washington. So 1.1 million square foot warehouse. And within this warehouse, design temperature 40 and outside design 0. When we looked at this, there's a minimum ventilation requirement of 120,000 CFM. And so the total building heat load in this case would be 3,525 kilowatts. And when we look at, according to the EPA, Washington has a CO2 emission rate of 602.1 pounds per MWH, and then also a natural gas emission rate, or a CO2 emission rate, rather, of natural gas of 399 pounds per MWH. And so we'll just keep these 602.1 and 399 in mind as we jump to the next example. Those are just inputs from the EPA. When we compare the carbon output first between resistive heat versus thermally efficient direct fired gas heat at design conditions for this example, recall the design conditions of 3,500 kilowatts. So when we look at what this equates to for applying electric heat, pounds of carbon would be around 2,100 pounds per hour. For gas heat, what we're looking at is 1,529 pounds per hour. And so that equates to a 38.7% reduction, or increase rather, compared to direct fired gas heating when you're comparing electric resistive to direct fired gas. So you're actually adding more carbon output by switching to electric in this case. Now, let's take a look at energy costs, because that's also an important aspect of this. And running through just with our baseline assumptions of cost per therm and electricity costs per kilowatt hour. Electric heat equates to approximately $423 per hour, and gas heat would be $196 per hour. And so this equates to 116% increase in cost. So just massive energy usage differences between these two options. Let's dive into an example from an electrical amp requirement. So this is a really important consideration. How do you get the power to the facility? What does that look like for an end user if you're heating with 100% efficient electric resistive heat? So ultimately, it looks like over 4,000 amps of power amp requirement, current requirement, and really thinking about this, what does it look like for our electrical grids? How does it look to handle a transition to electric heat in the warehouse and industrial sectors, especially as things like data centers, artificial intelligence increase, and the electrical needs surrounding those become more forefront and stress our grids. There is a place for both electric technologies and gas-fired technologies in decarbonization and electrification transition. So let's jump in. We're going to pivot here a little bit at this point and talk about a few projects, just a few examples where the technology has been applied and have had success working with a customer. So in this case right here, what we're looking at is a mountaintop facility in Canada. And so with a long list of challenges. So they're looking to provide the right amount of heat for workers and equipment inside. And as you can see here, there's a gentleman, I think, on the left-hand side here. So the scale of the building height is quite large, 120-foot tall facilities. They need to keep up with the -50 F design days, all while using virtually no indoor space. So it's quite the challenge. There's a large volume, and really this is a mining facility, Bighorn Mining. They're trying to also reduce contaminants in the air. They want to de-stratify the space. They really don't want to just be heating the top end of the space, of course. So designing a system for this facility, it's important to address both the heating and ventilation needs. So those are considerations. They had 3 buildings in this particular opportunity. And really, it was going to take a massive amount of BTUs when they were approaching this from a original design perspective with multiple pieces of equipment to achieve this, multiple different types of equipment. So for reference, the original design included 4 gas-fired units, 4 control panels, 4 destratification fans, relief air dampers with weather hoods, lots of ducting, extensive crane and hoisting equipment, and also man lift aerial work platform type effort. And really it involved extensive installation, extensive costs, and potentially even an inefficient design. And so when we evaluated this, we were brought in to evaluate this opportunity, really came down to, for one of the buildings, 4 units, and for another of the buildings, 2 units. And then for the last building, just a single unit, and really no ductwork or indoor space required, eliminating a lot of the extra needs, and really dramatic results with the high velocity, high temperature discharge at destratifying. And interestingly, the solution was actually a lower cost across all 3 buildings than the original single building design, which is just a fascinating example of the value that this can provide in these types of applications. And really the energy savings is also dramatic for the operational cost.
So hey, Nathan, you got a window on the left side of your screen, I think, is blocking some of the text.
Thank you, sir. Appreciate it. All right. So looking at the 20 to 70% expected versus conventional savings, the owner saved $1 million on install and seeing major savings in operation. And this 20 to 70% was based on a DOE study and building studies, which, depending on building location, application, and installation, these are the kind of results that would be expected in the field. All right, let's move to the next example. So this example is a million square foot automotive manufacturing plant, specializing in high volume underbodies for automakers like Ford, General Motors. And they needed heating and ventilation solution to offset robotic welding stations. So a lot of robotic welding going on. For example, they produce approximately 740 million spot welds per year, or 37 welds per second every day. So there's a lot of volume of welding going on in this facility. And the original goal, as you looked at this facility, was to support 20 robotic weld stations, which expanded to 50 over time, but originally provided a number of units which met this need. And as is common, as the supplier expands the facility, eventually growing robotic welding stations, they realize they have a problem. They potentially add exhaust when they add more welding stations without the necessary ventilation. And so what that equates to is some cold months in the winter, and you really need to look at the environment and what was changed within the facility when these types of things occur. And so we evaluated the equipment, learned welding stations moved from 20 to 50, and also learned exhaust was increased. And basically to bring that back into balance, we did a building study to evaluate their needs and learned quite a bit. So we added some dedicated makeup air units. They had 9 units already on the roof, or we added 9 additional to the 9 already on the roof and offset that exhaust without disrupting their current operation. And really this improved their IAQ compliance. It returned target temperatures to where they needed to be and allowed us to provide scalable solutions for facilities. All right, and we're going to pivot here to a little bit of a different challenge than we've discussed so far. So we're looking at this facility, which is in Cleveland, Ohio, a typical manufacturing plant, founded in 1903, been around for a while, producing steel ceilings, manufacture of billboards, even equipment cabs and gravity chutes, all kinds of different custom manufacturing. And you can see they've had multiple expansions, different buildings, an interesting mix. And how we were involved, we originally had included and provided them 2 units for the building on the foreground there, 2 heating units to temper that space during the cold winter months. And what we found was during the summer months, they were having some challenges with lots of things that manufacturers encounter, whether losses from turnover due to the difficult working environment, losses of productivity. For instance, for every degree over 77, studies have shown that productivity decreases by 1%. Not to mention the cost to safety, potential safety risk as people are in these environments working, and then also the cost of quality. How does quality change as an employee is in a better environment, and what that means even as they go home to their families and how they can show up for their families at home. And so we were brought in to find a way to potentially provide temperature relief. They had a decent amount of welding and those kind of things process internal heat gain. And so we decided to look into their facility. So let's take a quick top view and we'll zoom in here. And we're going to just focus on this part of their building. So if you can see here, the light pink would be building 1, and the green would be building 3, and the yellow would be building 2. And really wanted to focus our efforts on building 1 at the top. When we looked at this, you're trying to evaluate, okay, step 1, what are the needs of the facility? What are the inside factory temperatures? What are we trying to get to? And a lot of these facilities solve their problems just through ventilation. So they have a large exhaust load, and they either have open doors where air is coming through, and you're really trying to drive that temperature down to as close as possible to the outdoor air temperature, which is much better than no ventilation. It's much better than not doing any of these things, but it still can be difficult if the temperatures are up in 95 or 100 degrees Fahrenheit. And so after researching options with the customer, we decided to use a 2-stage, and we'll jump through here. These are our heating units originally, and we decided to jump forward and use 2-stage evaporative product here. So those are shown here in the blue, and those are really effective in these spaces. Depending on the humidity of the space, you can either cycle from indirect, which would be sensible cooling, or adding even a 2-stage direct to the facility. And what we found was, and the orange here, the exhaust, what we found was in this facility, we would hold around 77 degrees when outside temperatures were low to mid 90s. And This equipment uses a plate heat exchanger with outside airstream. In drier climates, even, it can be more effective as well. And one of the tremendous benefits of this equipment is that you already have the ventilation needs. So this is really a ventilation driven piece of equipment, and you're really trying to just knock some of the difficulty of the outside air conditions off, so the load to the building is just slightly less. No mechanical cooling needed, very energy efficient, and this can be a tremendous savings for the customer from an operation standpoint, from an overall cost of both install and then operation. And with that, we'll jump over to what questions we have. Would love to hear any input, any questions that might be on our mind today.
I see we got one in the chat from Ali. We can go ahead and tackle that one right now. His question was, can we prove that if we put the unit outside on the pad, instead of putting it up on the roof, we will have less vibration and noise into the building? And that's a good point, Ali. So while there are ways to mitigate vibration and noise for roof-mounted equipment, that can sometimes get complicated and expensive. Putting it on the pad is a great way to avoid that vibration and noise going into the building. You'll still have some noise from the fan, as that noise from the fan goes into the building, and the noise surrounding the ductwork and the vibration surrounding the ductwork. But if you use vibration isolation effectively on a pad-mounted unit, you're going to get very, very minimal vibration and noise entering the facility. Because that unit's going to be completely isolated from the building, you're not going to have that building up on the roof potentially shaking. There are ways to mitigate that on a roof-mounted unit, but putting it on pads is really the easiest way to do it in most cases. Wonderful.
What other questions come up as we think about either direct fired heat, as we think about ventilation driven solutions in these large spaces, or even evaporative cooling?
You guys must have covered it all too well. No questions popping up.
I think so.
We'll leave it open for a few minutes if anybody has some questions, but pretty much wrap it up there. If anybody
Absolutely.
thinks of something down the road later today, just kind of your mind's working, you can reach out to your local Odell rep and kind of get in contact with Nathan and Jacob and answer your questions. Anything you need.
Absolutely. And we'll just hang on here if those with questions come up. We're happy to stay on, and otherwise appreciate you guys joining today, and please let us know if we can help with any of your applications or technology.
Do you want to tackle that question in the chat, Nathan, or do you want me to tackle that one?
Yeah, absolutely. Great question. Appreciate that, Abraham. Yeah, so we do approximately 10 to 20% of our applications are customized. And so we do have a standard product line, which allows actually a lot of customization for controls and things of that nature. But we do offer both DX, chilled water, additional options to our direct fired equipment. Among other things, we're always evaluating needs of customers, and we do have a custom engineering team that can allow us to do more custom projects as they may come up. Great question. Neil, with a very timely question for all of the developments in heat pump right now. Absolutely. So we are currently, as part of the new product development team, even yesterday, we were adding heat pump to one of our new products, which is not released at this time, but we're looking at heat pump, what that looks like, as that is in high demand. And so we want to provide that in the future. Currently don't offer that, but expect to over the, I would say, next 6 months, a year. I'll just give a quick plug while we're all here. We love to discuss our technology further with anybody who has a specific application. Always available to jump on a call. We enjoy breaking this stuff down into the nitty-gritty details. So feel free to reach out if something like that makes sense. If you have additional questions, we love diving into the combustion and understanding the byproducts of combustion. I know those are common questions. How do we manage that? And so we have a safety standard. Our equipment certified to a CSA standard for direct fired heating, which manages that. And we have periodic testing to ensure that we are inherently safe for everyone. And this is just a great part of being able to communicate the value of this product and include others.
Yeah, it seems like we probably got all the questions in that are going to come. So thank you, Nathan and Jacob, for your time and for the great presentation. We'll shut it down there, and thank you everybody for coming. Thanks for taking time out of your day. Have a good one.
Thank you.